All right, ladies and gentlemen, we are going to begin chapter 6. So, we will start with 6.1, which deals with angles of polygons. As usual, feel free to pause, write down whatever you need to at any point in time so that you can continue without too much of an issue. So, first, let's start with the idea of a diagonal. Now, a diagonal is a line segment that connects two non-consecutive vertices. If we look at a triangle, it's not possible to put a diagonal in a triangle because every vertex is consecutive, meaning connected by a side of the polygon to every other vertex. But if we look at other shapes like the quadrilateral, the pentagon, the hexagon, the septagon or heptagon, and octagon, that is a little bit different. So what we're going to do is we're going to use these figures in an effort to actually do more of a discovery-based concept. So we're going to start just by numbering the sides in each figure. All right. Nothing special. All we're doing is counting the sides. That's it. All right. And then what we're going to do is we're going to talk about how many triangles we can make by drawing diagonals in. Now, here's the rule for drawing diagonals. Number one, all diagonals must start from the same vertex. Number two, diagonals are not allowed to cross each other. Okay? Now I can't draw any diagonals into a triangle, so there's only one triangle there. I can draw one diagonal in a quadrilateral. The reason I can't draw the second diagonal is because then it would cross the first one, and that one diagonal broke the quadrilateral into two triangles. I can actually draw two diagonals in the pentagon, and that breaks it up into three triangles. So you can kind of guess where this is going. I can draw one, two, three diagonals in the hexagon, and that breaks it up into four triangles, and so on. We kind of expect what we're going to see next. So we draw in one, two, three, four diagonals, that breaks it up into five triangles, and then we draw in one, two, three, four, five. One, two, three, four, five. Yep, it looks like five. Okay, five diagonals, and that breaks it into six triangles. Now, why did we break them up into triangles? The reason we broke them up into triangles is because triangles are something we know how to deal with. We know that the sum of the angles in a triangle is 180. So this leads to the idea that, okay, really what I'm saying is, since we know the sum in each triangle is 180, if I have two triangles, then the total number of angles I have has to be 180 times 2, which is 360. And if I have three triangles, it's got to be 180 times 3, which is 540, and so on. So we're basically just saying, okay, well, four triangles times 180 is 720, five triangles times 180 is 900, six triangles times 180 is 1080. So this leads us to the idea of polygon interior angle sum theorem. And that basically says if I want to find the sum of the measures of the interior angles of a convex polygon, I take n, which is the number of sides, minus 2, times 180. That's it. Done. Now, this does not tell you what one individual angle is. It simply tells you what the sum of the measures of the interior angles are. So we're going to start with the one that would basically be next in our pattern, the idea of the nonagon. So first of all, here's our nonagon. A nonagon has 9 sides. That means n equals 9. So if we go to our formula, n minus 2 times 180, that's 9 minus 2 times 180. So 9 minus 2 is, of course, 7. 7 times 180, this is what they invented the calculator for, 1260. Now, do I know how much each individual angle is? No, not at all. But I know that when I add them all up, I get 1260. Now you're going to notice every one of my examples so far has been a regular polygon. This works for polygons that are not considered to be regular. It's just easier to draw the regular polygons for the purposes of coming up with an example. All right, moving on to our next one. Again, pause and write down whatever you need to. So the aliens that invaded in Chapter 5 basically have built malls, but for some reason the food court is shaped like a regular pentagon. So basically, you got a bunch of hallways coming together into this food court, and what they're asking us for is they're saying, hey, find the measure of one angle. Now, find the measure of one angle in a regular, the important word there is regular, pentagon is very easy. Let's start with our formula. We know a pentagon has 5 sides, and we have our formula of n minus 2 times 180. So we plug in, we already did this, we know the numbers for this, we got it before, that's 540. Well, great, all the angles add up to 540, but I only want one of the angles. Well, because I only want one of the angles, there are 5 angles. In a regular polygon, those angles are all congruent, so that means those 5 angles are all going to have the same measure. So I take my total of 540, I divide it by 5, and I get 108. So one angle has a measure of 108. Now, we can also use this formula to go a different route, and that is the idea that we can actually try to figure out, uh, based on the measure of a single interior angle, how many sides the polygon has. So that's going to be our next one. Now, here's the difference. We know we're going to have our n minus 2 times 180. That's kind of a given. And we know that that's got to equal something. So the big question is, what does it have to equal? Most people are going to say that it has to equal 150, and they're very, very close. The truth is it has to equal 150n. Here's why. All right? If I say n minus 2 times 180, that's the sum of the measures of the interior angles of this polygon that has n sides, and I don't know what n is. But what happens is I say, well, okay, I know one of the angles is 150, and if I multiply 150 by n, then that means I'm going to get my sum. So, okay, now we distribute, and we have a pretty straightforward equation. I'm going to subtract the 150n from both sides, and just for the sake of saving space, I'm going to add that 360 to both sides. We divide, and it tells us that it's got 12 sides. That's it. Very simple, very straightforward. So if I were to give you the measure of any exterior angle, excuse me, interior, I apologize, I said exterior because I know what's coming next. So if I were to give you the measure of one interior angle of a regular polygon, whatever it happens to be, I mean, if I just picked a triangle, we know that's 60, that's real easy. Basically, just plug that in where you see that 150, distribute, clean up, solve, and the answer will pop right out. It'll tell us how many sides the polygon has. And don't forget, a 12-sided polygon is referred to as a dodecagon. We should know that. Now, if we have interior angles, we also have exterior angles. So I'm going to take this familiar shape that we see right here. These are the same figures that we saw before. And what I'm going to do is I'm going to construct exterior angles. Now, the way we construct exterior angles, all right, is we basically say, all right, well, we're going to extend every side of the polygon in one direction. And you can see we kind of have that iris look to everything. We've extended all the sides in the same direction. You don't extend the side in both directions because if you do, then you don't have exterior angles. So you want to create one angle on the outside of the polygon at each vertex. So we're going to start by filling in a little information that we already have that came off of that first slide. This is just the sum of our interior angles, something we already know, something we already calculated, okay? Now let's think about this for a second. Every vertex has one interior and one exterior angle, and they form a linear pair. Linear pairs add up to 180. So what that means is that I have 180 degrees 3 times in a triangle, all right? Because I have an interior and exterior at each vertex. So if I take 180, I multiply it by 3, I get 540. Now if I do the same thing for the quadrilateral and I do 180 times 4, I get 720. 180 times 5, I get 900, and so on. So basically I'm just going to go through and multiply 180 times the number of sides. So the blue numbers are the sum of the interior angles. The red numbers are the interior and the exterior angles together. So if I have the interior and I have the interior and the exterior, and I want to get the exterior by itself, I simply subtract. Now the interesting thing that happens is when we subtract, in every single case, we get exactly the same value. It never changes. So that gives us polygon exterior angle sum theorem. The sum of the exterior angles of any polygon, no matter how many sides it has, always 360. Every time, never changes. I don't care if it's got 10 million sides, they add up to 360. It's got 3 sides, they add up to 360. All right, does not matter at all. So let's basically use this idea, and we'll come along here and we'll say, oh, we got a whole bunch of angles and we got to add those angles up and we got to see what we get. Well, what do all the angles add up to? They add up to 360. So I add them up and I clean it up. That's just a little algebra 1, combining like terms. And I solve for x. Very simple, very straightforward. That's it for section 6.1. The problems that you have to work on are located on school wires under chapter 6. And if you have any questions, we will deal with them when we get back. Remember, hopefully as you went through this, rewind it, pause it, write down any notes that you need to, discuss it with your classmates, and we'll deal with it when we get back. Thanks very much, and hope you understood it all.